Good evening to all of you. We are back again with another exciting session. I, Ajay Jha, on behalf of ACS India team, welcome you to today's ACS Science Talks session. Today, we are pleased to have Professor S.N. Tripathi with us. So, Professor Tripathi is currently higher administrative grade professor at the Department of Civil Engineering at IIT Kanpur. He is also an adjunct professor at the Center of Excellence for Research on Clean Air, IIT Delhi. He obtained his PhD from University of Reading, UK. Thereafter, he was a postdoctoral fellow at the prestigious University of Oxford, UK. Professor Tripathi's research is focused on air quality, climate change, human health, and nuclear reactor, and some of them he would be talking today. He has numerous awards and accolades to his credit, to mention a few: prestigious Santi Swarup Bhatnagar Prize, Nasi Scopus Young Scientist Award for highest citation in earth sciences, UP Ratna Award by the government of Uttar Pradesh, and many more. He is the editorial advisory board member of the ACS journal Environmental Science and Technology Letters. Professor Tripathi is a member in various high-level committees of Government of India, and he is also associated with the Center of Environmental Science and Engineering. So before Professor Tripathi starts, we have a couple of instructions for the audiences. We request the audiences to put their questions into the Q&A tab on the Zoom window. Kindly avoid putting questions into the chat box, and in case of any internet issue, please stay with us. Now I would like to invite Professor Tripathi to deliver his talk. Over to Professor Tripathi, please.
Thank you, Dr. Jha. Thank you very much. Thank you, ACS team, for giving me this opportunity to talk about some of our work, which we have been doing for last about a decade. And the work I'm going to talk is India-centric, not that organic aerosols are not found or studied elsewhere, but we know that just to put the things in the context, in the Indian context, because as you will see that these are going to be a very pivotal component of our strategy to clean the air. So that constitutes a large part of PM 2.5, that is particulate matter 2.5, less than 2.5 micron diameter. And we know that a lot of emphasis has been given on mitigation of these tiny particles which are injurious to human health. And in addition to that, they have other adverse impact on climate and properties, etc. So what I will do in next half an hour or so is to take you through with some basic about particle size distribution and how the precursors and their sources, which eventually give rise to nucleation and growth of secondary organic aerosols. And then I will talk about what are other atmospheric processes that contributes to formation or transformation of these tiny particles, with a focus always on organic aerosol. I will talk a lot about their chemistry, and then I will discuss further about how they exert a forcing on climate change via their optical properties, their hygroscopic properties, and then finally I will conclude with some of their impacts which we have evaluated basically in terms of discoloration of some of our monumental heritage or how they impact human health. So this work, what I'm going to present, has been done by my couple of PhD students and postdocs in last about 8 or 9 years. And there are several collaborators from India and abroad. So there are quite a few. So I am not going to list them here. And some of this work has been generously supported by IIT Kanpur, Department of Science Technology, Department of Biotechnology, India-US Science and Technology Forum, and Central Pollution Control Board. So some of the recent work has been supported by these agencies. So this is a view graph, just to, this is more like a primer, that what you see here on the x-axis, you have basically three kind of sources. You have anthropogenic sources, basically that combines different kind of activities that gives rise to gases or particulate matter directly sometime. So what you see here, there could be power plant or traffic sources or cooking, which is happening in the offices or residential houses. And then what you see that you have rural sources where some different kind of sources operate, maybe agriculture practices or dairy farming or other stuff. And finally, what you see that you move away and you have thick forest lands, and that which comes from the forest area or trees, we call them biogenic sources. And what you see on the y-axis, basically 3 arrows you see, and what we start with emissions and generation, that how they get emitted. And then the second arrow shows that what happens once they are emitted in the atmosphere. So their chemical and physical transformation, what kind of processes take place. They are both related to chemical changes and there are also physical changes involved. And then after that, what happens that how they are going to exert or change, modify some of the important meteorological, weather or climate related processes. So what you see here is that from these sources, you have a variety of gases that come out. You have VOCs, volatile organic compounds, you have ammonia, sulfur dioxide is a very important component. And you also have these inorganic species, for example, carbon monoxide, then you have greenhouse gases like carbon dioxide and NOx, and a huge range of basically VOCs, which are isoprene, terpene, etc. They come from biogenic, like forest kind of sources. And some of them are basically precursors to secondary organic aerosol. The SOA word will come a couple of times, and that's called secondary organic aerosol. And from there, what would happen that it would go through oxidation, because atmosphere you have lots plenty of oxygen and ozone, and you have also hydroxyl radical. So that's going to oxidize through a variety of chemical reactions, and that would give rise to new particle formation. And the new particle could be multi-component or a single component particle. It could be either semi-solid in the phase to begin with, or it could be only liquid. That depends on its precursors, the state variables, that is temperature and RH, and also amount of other trace constituents which are going to be in the newly formed particles. And then further heterogeneous reactions are going to happen on the surface of these multi-component, multi-phase particles. Multi-phase means that there could be a part liquid and part solid. And then if some reactions take place, vapor phase chemistry takes place on the surface of these particles. So then we call basically particle surface oxidation. And then subsequently, what happens that these particles or droplets are going to stay in the atmosphere, and we call them chemical aging, because their age is increasing, the residence time is increasing, but some kind of chemistry is happening. And after that, if a bulk oxidation happens, then it would give rise to fog formation. And on the fog, where the nuclei, which acts as these organic particle, that can get removed by wet scavenging, or if it gets lifted in the atmosphere, it crosses the lifting condensation level, then it would form cloud. And you know that now cloud can interact with the radiation, then thereby it can exert a forcing on climate, or by itself, these organic particles can scatter or absorb solar radiation, and by so doing, they can also perturb the Earth atmosphere radiation budget, and therefore they can cause a climate forcing. So there are a variety of atmospheric regions, or to understand the impact on atmospheric processes, we need to learn about this particular part of what we call as PM or aerosol, which is the organic aerosol. In a slightly now different way, what I'm going to show you here, that what is the overall range of size in which these particles are found. So what you see, you have a plot here on the right hand side, and on x-axis you have diameter that ranges from few angstrom, that is a fraction of nanometer. Then you see 1 nanometer, 10 through 10,000, that is 10 microns. So there's a very wide range of sizes in which particulate matter is found in the atmosphere. And what you see that on the very top, there is a black curve with different modes. And these modes actually correspond to different diameter. So you see the smallest mode, we call it as a nucleation mode. That is gas to particle formation occurs in this mode, and which lies between about half a nanometer to 2 or 3 or 4 nanometer. And the next one, what you see is a Atkin mode, and which lies from about 10 nanometer to 100 nanometer, and then followed by accumulation mode, which is from 100 nanometer to about 2000 nanometer, that is up to 2 micron. And we call it accumulation mode because through any processes, they are most difficult to remove from the atmosphere. And that is why they tend to accumulate, and hence this name. And finally, you have a coarse mode, that is a very large size particles, which starts from about 2 micron to about 100 micron or so. And you see that each one of them are associated with a different process. So nucleation mode necessarily will form from gas to particle conversion, right? So it's a phase transition process. So you have to understand a lot about the thermodynamics and other state parameters of the gases in order to predict nucleation rate, etc. It's a very complex chemistry. I will dwell upon that in subsequent slides briefly. And after that, you can have a variety of microphysical coupled with chemical processes. For example, these tiny, very tiny droplet of aerosol can aggregate and then can further coagulate to form these large droplets. And then further, they can give rise to accumulation mode. And if you look into very distinctly, the coarse mode is formed from directly emitted particles from dust or sea salt, etc. And on the top, what you see here is that there are 3 kind of further processes which are listed. You have basically a nucleation, where the gas molecules are coming together, aggregating and forming critical cluster, which is going to last. Then you have condensation. There is a droplet on which gas molecule is coming and leaving its energy, therefore condensing on its surface. And then couple of these particles coming together and therefore aggregating and then further coagulating, which is basically colliding and coalescing, and that is called a coagulation process. So it's a very complex, basically sequence of what we call microphysics coupled with chemical processes. So I will begin with first some of the work we have done on the formation of organic aerosol. So this is work what we did a couple of years back over Kanpur, and we looked into the new particle formation events by using a set of instrument called scanning mobility particle sizer, which measures particle size from few nanometer to about a micron. And what you see in the top panel, what you see that there are those diagonal emerging banana shaped curves. These are called, if you see closely, they look like a bent banana. What you find in this plot, basically on the x-axis, you have different dates. On the y-axis, you have diameter of particle running from 3 nanometer to few hundred nanometer. And then there these colors show, you see dn by d log dp, that is their number. And what you see that every day from the morning, you see there is a steep rise, the black curve, black line, if you notice, that is the diameter of particle, and then it starts from about few nanometer, and then slowly it rises to, just a minute, I forgot to record. I think I don't see, here is it. I don't see the recording mode. So I just want to tell you this.
Okay, no issues. We are recording from our side. It's okay, Professor.
Wonderful, thank you.
No issue.
So what
Please go ahead.
Every day there is this, that rise particle form and then slowly rise or grow from few nanometer to about 100 nanometer or so. And this is a very interesting, it has happened all across the April. And we tried to look by using mass spectrometry. So mass spectrometry can give you in real time, size-wise, chemical composition of particle. And our interest was mostly to look into their organic composition. And what you see there, that's just to give an idea, this pie, a great chunk of this pie is pink. So most of these very fine particles, less than few hundred nanometer, were comprised of mainly organics, right? And further, if you look into this right bottom plot, what that shows different kind of chemical families. So these are all basically fragments. And what we found in Kanpur, that a lot of them are comprised of amines. You see that most of them have nitrogen coupled with these organic compounds. So mostly these come from automobile exhaust. So this was a very interesting thing that we found over Kanpur. Some time back, we also did a study during winter time over Kanpur, and we were looking at some of the data of particulate matter when the fog forms. And what we found, that there was a very interesting pattern emerges, that there was an enhanced formation of secondary organic aerosol. So what I'm showing here is only a very simple plot, which goes as a table of content in ESNT. And that shows here there's a black curve, and then there is a red curve. And the red is for fog time, SO is for secondary organic aerosol formation, and black is for clear days when there is no fog. And we clearly found that during fog time, there is a lot more formation of secondary organic aerosols. And what we also saw, that as you go from smaller to larger droplet, that overall content of organic aerosol decreases. So that was quite interesting, because this was a very simple study. This was not done using any very sophisticated instrument. And secondary organic aerosol was also estimated using filter-based organic aerosol method. So in that way, today we know that it has some artifact. But interestingly, we found that something very interesting is happening. So I have actually another very interesting slide as a follow-up to this. So this is a follow-up study, right? This was done by with my student Abhishek Chakravarti and with my colleague Dr. Gupta. What you see here, that there are two plots on the left-hand side, okay? And we name them as C, M, and F, coarse, medium, and fine, right? And there are two panels. The top one is giving about the amount of organics, nitrate, chloride, ammonium, and sulfate present in these three different size droplets. So we could actually very precisely collect droplets of these three sizes, and their sizes are mentioned here. So fine ones were less than 10 micron, the medium was 20, and coarse one about 25 micron. And then that covers a good complete size range of fog droplets found in Kanpur. And the bottom one, what we have done here is, we have given the amount of copper, iron, and water-soluble organic compound in these set of droplets. Interestingly, what you see here in the top panel, literally there is very little difference as far as abundance of these major species goes in as a function of droplet size, right? But if you look into this bottom panel, what you notice is there, as you go from coarse through medium to fine droplet, all three species, the two metals, copper and iron, and water-soluble organic compound increases, right? So you see there is a very little difference between coarse and medium, although there is a little, there is a difference, however little it is. But in the fine droplet, what you see, all three are present in lot more abundance than in the coarse and medium, right? So our hypothesis was that something very interesting happening in the fine droplets, which is causing abundance of water-soluble organic compounds, which is giving rise to secondary organic aerosol formation, right? So it seems like that these tiny droplets are a much efficient chemical reactor moving around in the atmosphere than these larger droplets. And the implication is that if they are forming more secondary organic aerosol, In fact, and they hang around larger, in fact, they would cause more damage in terms of visibility or human health, etc. So how did we actually test this hypothesis? We use a box model with sufficient chemistry. And what you notice here on the right-hand side, we have this time-dependent kinetics model of chemistry run for these three different sizes. So what you see on the x-axis, you have time. And on the y-axis, what is plotted is oxygen to carbon ratio, right? So this ratio we were able to obtain from measurements. So you have three dotted lines. You see 10 micron, 20 micron, 25 micron. So these are basically constant oxygen to carbon ratio measured by mass spectrometry. And then you see there are two sets of three curves, right? So you have black, blue, and red, solid ones, which are without incorporating the influence of iron and copper. That is, the Fenton chemistry was kept off, switched off in this. And then you have dotted curves exactly for those three droplets where Fenton chemistry was switched on. And you see that when Fenton chemistry was not switched on, there was some difference in O to C ratio, but that was very, very little, right? But the moment you switch it on, the difference increases. And in fact, O to C ratio also increases and comes much, much closer to the measured value. So this was a very interesting thing, what we found in this paper. And then there was a subsequent study we just conducted in Delhi. For some reason, I could not actually upload that slide. Slide has some problem. That we just conducted last year using a different kind of mass spectrometry, which is called EZ, that is electrospray kind of a mass spectrometry, which allows you to detect larger particles unfragmented, right? They allow them to, so that they don't fragment it, because in the usual mass spectrometry, what happens that very large particles get fragmented. So you are not able to get their chemical composition. On the other hand, EZ allows you, and we did find some very, very interesting further supporting information from Delhi that gives more insight to what is shown in this slide in this paper, but somewhat for some reason I'm not able to show that here. This is a result which is still very much is under brew. This is work which is done by my student Suniti Mishra, and there we actually deployed mass spectrometer and then chemical ionization mass spectrometer together with PTRMS in Delhi last year, 2019 winter. What I'm showing, I'm revisiting new particle formation, but I'm going to give a little more idea, and the story is still getting built into. So you are already familiar with this kind of a plot. What I told you earlier was a banana plot, where the new particle formation was happening, right? But what you see here, that no new particle formation is happening, right? So this is what I'm going to show you, that some very interesting results we found about new particle formation from our Delhi experiment. Instead of nucleation happening here in the right top curve, right? What we are seeing, excuse me, that there is a sustained growth of particle. If you look into this black line, in fact, we are not able to really determine that new particle is forming. Rather, the particles which have already formed, they are growing, and they are growing all night. We call it a nighttime growth. The nighttime growth of particles have not been obtained or seen at many places. In that way, it's quite unique. Now, if you look into, there are some crowded circles or pies below that. Very quickly, if you look, actually what we find that a good part of that is primary organic aerosol in nature, right? That's the main message from here, right? And then now if you look into that left-hand side, these panels, and most of these plots below the growth curve are basically obtained either from SIMS, that is chemical ionization mass spectrometer, or from PTRMS. And something very, very interesting is happening if you just look into maybe the second plot from the top. So what you see that there is during that time a depletion of gas phase nitric acid, and there is an increase in particulate phase. suddenly at some point of time, and at the same time it coincides with an increase in particulate chlorine and likewise particulate sulfuric acid, etc. Okay, so there's something happening at some point of time during night that is giving rise to a phase, basically transfer from gas to particulate, and that is the time when the growth is happening at a fastest pace. And that is what we find it quite interesting, and we are still looking into that, and we hope that it would be something which can be concluded in a very interesting way. This is just to give you another piece of work which was done by using mass spectrometer data again from Kanpur. And what we did here is that very few places in the world people analyze the PTOF data from a mass spectrometer, right? That is looking the size-wise chemistry data, right? Because what happens that the data is available, of that kind of data is available from other places, but the signal is weak because the overall amount of PM is not so high. So when you resolve them into different sizes, then you don't have enough or sufficient signal to noise ratio. And what we could see by looking into the PTOF data, I would just point you out that two broad class of families we looked into of organic aerosol. You see, one was that semi-volatile oxygenated organic aerosol. Another was cooking organic aerosol, right? Left-hand side and right-hand side. And they are mainly comprised of these fragments, right? And we found that there is some very interesting differences in their size distribution. If you look into the bottom, right, one has a smaller, and that is statistically significant. One has a smaller size, another has larger, right? So these have some very interesting implications to the growth and other things of what you call organic aerosol, right? I would now switch from formation and growth to the sources of organic or secondary organic aerosols. So this work was done by doing measurement at Kanpur about 4 or 5 years back. And the two view graphs, what you see are, one is for a non-foggy period on the left-hand side, and the right-hand side is foggy period, right? And these are basically a set of back trajectory which starts from Kanpur. If you come at the very bottom point, and you can actually build them back in different pies. So that really tells you that how the composition of PM changes as it was transported through different places to Kanpur. Okay, and there's some very interesting differences we found during non-foggy period and foggy period. Primarily during foggy period, we found that, which is I have listed here, that you have a lot more contribution from biomass burning stuff. And that is what was very interesting finding from the measurement over Kanpur. This is just moving on with the sources over Delhi a little bit. This is a very recent work we conducted, the result from the study conducted over Delhi. And that shows that how the PM composition over Delhi changes over a period of January through May. And what we see that there are very high amount of PM during January. On the x-axis, you see it is January here. And we also found we could further resolve into different kind of sources, and that I will show you in the next slide from 3 places. So this is a work which is still under consideration. So again, the technique is same. The 3 mass spectrometer were actually deployed at 3 sites. One is what you see at the central north of Delhi, Rajendra Nagar. Another is IT Delhi, and third is the downwind side at Mano Rachna. And we could really get a wintertime complete source characterization of organic and inorganic aerosols over Delhi. That some key differences, if you see here, are basically that, for example, you look, IIT Delhi has a much larger contribution from hydrocarbon-like organic aerosol, which is, that is called more like traffic generated aerosol. So these are some interesting information which is which would have some value from the air quality management point of view. I will skip this slide just for the interest of time. I will now come to some of the work what we have done related to environmental impacts of organic aerosol. So this is a work which some of you might be familiar with, that we wanted to understand what chemical species are causing discoloration of Taj Mahal. And for that, we actually adopted the traditional way of sampling particles, bringing them back to laboratory and analyzing them, while also collecting them on some small grids so that we can expose them to some microscopy kind of technique to get the particle size distribution. And using that, what we see, what we show here is the particle size distribution. And then using the distribution and chemical composition, we could actually work out what is the turbidity of this particulate layer which deposits on Taj marble surfaces. And what then we did, we had put couple of surrogate marble surfaces in Taj Mahal, and by doing simulated opacity and looking at those soiled surfaces, we could work out that what are the species which are contributing most to the haziness or murkiness of these marble surfaces, right? And as a follow-up to this work, we did some very simple modeling study where we evaluated impact of two major sources. One was solid waste burning and another was dung cake burning. And we could see or estimate that it is the municipal solid waste MSW which is contributing a lot compared to the dung cake burning to the soiling of the iconic Taj Mahal surfaces in Agra. So this work actually became a cover page article of ESNT, and it has some interesting implications to the policy making in Agra, because the Parliamentary Panel on Science and Environment took cognizance of it. They made a visit to Taj Mahal and brought certain kind of rules and enforce it in order to, decelerate or stop further discoloration of Taj Mahal. This is now, I am now changing it to a little bit of climate impact of these organic aerosols. So this is a work we conducted with our colleagues from PRL, with Dr. Neeraj Rastogi's group. So what you see that from 16 winter, we are plotting here on the y-axis is water soluble organic compounds, carbon, and on the x-axis is basically their absorption. Their absorption is very important because this is one thing which enters into computation of their optical properties and therefore how much they exert the climate force. So this is a very interesting piece of work which we actually did with some real-time measurement. And the values are here, but what you see that there was a rain event, and after rain event, how it actually again just got up. And at the same time, we also applied a hybrid technique where we did some additional measurements, and using that, actually we can compute some very, very important fundamental properties of these organic aerosols. So what you see here actually are absorbing refractory indices. And these are, once you have that and people try to characterize, this can be fed into regional or global model in order to estimate the climate impacts of these particulate matters. And then we actually try to look into some of the impacts they have in terms of when they coat. So some of you might be knowing that these organic aerosol can form coating over black carbon. And we try to look into how those coatings influence their overall absorbing capacity. And that is the work what we actually put in this. Interestingly, what you see here is that how at 365 nanometer, that is in UV, you have very high absorbing coefficient, or basically that absorbing refractive indices of water soluble organic compounds. So these kind of measurements are available from very few places, and that is one of them being Kanpur. And then what we also did using this work, using this kind of estimates, we tried to work out that during biomass burning event, how much exact radiative forcing these kind of aerosols put on the top of atmosphere. Remember that a lot of effort what climate scientists currently put, and if you see, many chapters are devoted over last several IPCC reports about understanding and refining the radiative forcings of greenhouse gases and particulate matter. So in that way, this work has a lot of importance, that we could work out that what is the total forcing of overall organic aerosol of top of atmosphere. That is what you see here on the left hand side. And on the right hand side, which is a more important plot, where we show that during biomass burning, how this forcing is perturbed. And interestingly, what you find that because we have a lot more absorbing kind of organic aerosol in our emissions, and that is why you have relatively smaller cooling. Otherwise, organic aerosols cause a lot of cooling on the top of atmosphere, but these kind of aerosols what are emitted here, and these are all based on the measured estimate what I showed earlier, these cause a relatively lesser cooling, or in other words, they would warm relatively, okay, the atmosphere. This is also related to, again, the climate related connection of organic aerosols. So many of you know that these aerosols are also studied a lot because of their connection with clouds, right? So they can modify clouds, and that a great deal of work has been done about that, what we call as indirect effect, so-called indirect effect, right? What I'm showing here is a very important property. So what people generally do, that they try to measure cloud condensation nuclei ability of particles. And that tells you that for a given weather conditions, whether a particle will form a cloud droplet or not. But that's a very tedious thing. That requires measurement of CCN across the globe for different weather, etc. What has been the practice recently, that if you could measure chemical properties, you could effectively get a single lumped parameter which is called hygroscopicity. And this alone can give you a good idea about CCN ability of particulate matter. And this, in this work with Dr. Deepika Bhattu, who is currently a faculty at IIT Jodhpur, she was my student earlier, we were able to get a very good empirical estimate of this total hygroscopicity as a function of oxygen to carbon ratio. And we found that if you see, there are a lot of noise in this data, but still some trend is emerging. And that's a very interesting part of this work. I'm almost now on my second last slide. So this is a recent work which was done in collaboration with people from US, UIC, from PSI, PRL, and other colleagues, where we again use this all real-time measurements to connect it with the real-time, again, which was first time done in India, that their ROS property. And the ROS, which is reactive oxygenated species, directly tells you the oxidative potential of these particulate matter. Why they are important? Because higher the oxidative potential or higher is the OP, higher or they can damage your cells, lung cells, to the greater extent, right? So particulate matter with higher OP are not good for your health. And that is what was measured, and this work just got published 2 months back in Environmental Science and Technology letter. Briefly, the finding from this study is that we found that OP in Delhi particulate matter is 5 to 10 times more than what they have found from some places in US, right? Finally, this is my last slide. So in an earlier work where similar kind of thing we measured, from some other places in India. So what you see that on the left-hand side was an assay, what was just stated in the previous slide, which is DTT. And on the right-hand side, you have a different kind of assay. And on the x-axis, you have 2 or 3 different kind of emissions. You have fresh trash burning and you have ambient aerosol. And if you look into the DTT activity of trash burning, that seems way higher than ambient aerosol. So that is how you can get some idea that if you are exposed to a trash burning close by where you are walking or doing something, it's not good for your health. So I will just stop here and will like to now see what are the questions I have. So thank you very much. So let me now see